Hello all, this is the Pencrest High School AP Physics 1 video series. This is video 1J, Relational Motion. Now relational motion in some ways is the most difficult application of kinematics. It's called relational because typically what we have is two objects moving at the same time, and the trick is to establish the relationship between the two objects' positions at some time. The relationship that you have to establish is specific to a particular problem. You could be presented with two objects that are moving towards each other from some initial separation, or something is chasing something else and catching up to it, or maybe they're moving away from each other, or any other conceivable option. The trick is to combine what you know with when and where something happens, where they meet, when they meet, when they're separated by a certain amount. We're going to look at several of them. So the when and the where are associated with the time and the position. So we're going to end up with a system of equations, two equations and two unknowns. How you solve the system is up to you. You can use substitution, you can add or subtract equations, you can use matrices, you can set the equations equal to each other. How you do it is up to you, whatever you're most comfortable with. Now we're going to look at the steps involved. First, we set up a kinematics table with a column for each object in the problem. Two, we determine the relationship between the final positions. This is the physics here. Do the objects meet? Are they separated by some predetermined distance? Do they travel the same distance? Does one object travel farther than the other? The key thing here is to have an expression for each object's position in terms of the same variable. So we'll see some examples of that. Third, is there a relationship between the two time intervals? Do the objects start moving at the same time? Does one of the objects start later? If so, that second object would have less time to move. So if there's a time lag, we would have t minus whatever the time lag is. Again, we'll see some examples of that. Step 4, write the kinematics formula for the final position for each object. So again, we're familiar with this formula already. Final position equals x naught plus v naught t plus 1/2 at squared. We're going to write that for each object, and then we combine the two equations somehow, solve the system of equations for x or t or both. Okay, so here's an example. You have a cheetah moving with some constant velocity v sub c, and we have a gazelle moving with some other constant velocity v sub g. The separation distance is s. We're going to put the origin where the cheetah is at this moment in time, and we're going to assume that v sub c is greater than v sub g. Now, assuming that v sub c is greater than v sub g, what's going to happen eventually? At some point in time and somewhere, the cheetah is going to catch up to the gazelle. When the cheetah catches up to the gazelle, they're going to be in the same place at the same time. We're going to call that this position x. So when they reach that point and the cheetah catches the gazelle, they will both be at position x. Now the cheetah, looking at the problem, the cheetah is going to have to cover more displacement in order to get to that point. You should be able to tell by looking at the image how much more displacement it's going to have to cover. Okay, now we can assume that the time intervals are the same because both animals are moving at the instant shown. This is when t equals 0. When the cheetah catches the gazelle, that's the duration of the interval. That's the t. We're also told that the origin should be where the cheetah is at this point. So here's my origin. Clearly the cheetah's initial position will be 0. If that's the case, what then is the initial position of the gazelle? Should be able to tell just by looking at the picture. They'll both end up here, so that'll be the final position for each of the objects, each of the animals. Okay, so here's the kinematics table. Again, we have all our quantities listed. We have one for the cheetah, one column for the gazelle. We're going to set up the relationship symbolically. Starting with what we know, both velocities are constant, so we know that initial and final velocities will be the same. We're given v sub c and v sub g as pieces of data, so they can go right in there. If the velocity is constant, we already know that the acceleration is 0, so for each of the two animals. Given the information in the image, we see that the initial position of the cheetah is 0. The initial position of the gazelle is s, the separation. And when the cheetah catches up at position x, they're both there. So there's our relation there. Time intervals are the same, so you can call them both t. So we're going to write the position equation, the final position equation for the cheetah. Here's the final position, initial velocity times time, 1/2 a equals 0 times t squared. So there's the cheetah. Here's the gazelle. Final position, initial position s, plus initial velocity times time, and again, 1/2 times 0 times t squared. We're going to simplify them both. We have those 0 terms, so we can get rid of them. This is the cheetah. Final position equals vc times t. This is the gazelle. Final position equals s plus v sub g times t. Now, this is our system of equations. The two things we don't know are where and when. This is a piece of data. This is a piece of data. This is a piece of data. The unknowns are where and when, x and t. So you can solve this a number of different ways. I would tend to, in this case, set the two equations equal to each other because they're both equal to x. So we'll set them equal to each other. Here's the cheetah, here's the gazelle. The final positions are the same. We're going to collect the t terms on both sides. So we'll subtract v sub gt from both sides. We get this expression here. We're going to factor out the t. We get the quantity v sub c minus v sub g. And then we're going to solve for t by dividing out this term here. And we get this expression here. So this represents when the cheetah catches the data, or the cheetah catches the gazelle. We're going to take that t term, put it back into the expressions for the final position to find out where it happens. All right, so here's another example. This is the standard relational motion problem. You'll find it in every book ever made, at least every physics book ever made. So we have train here, train 1. We have train 2. They're at city A and city B. They're going to start moving towards each other with constant velocities, v sub A and v sub B. Again, those are pieces of data. Cities A and B are a distance d sub t apart. So again, we can assume the tracks are straight and level. Well, we're going to put the origin here, at point at city A. And again, at some point in between, the trains are going to meet. We don't know where it is, but that's our job. So I'll give you a little less guidance on this one. Again, both velocities are constant, but in this case, what's different about train B? Think about its direction. The origin is established at city A. We then know what train 1's initial position is, what then is the initial position of train B. Look at the image and it'll tell you. Final position will be the same for each because this is where they're going to meet. So again, they'll be in the same place at the same time. Time interval is the same for each. We'll call it t. Write your final position equation for each train and then solve the system of equations. You should have some room on your note sheet at the bottom of the page there to set this one up and solve. Once again, what we're after is where and when do the trains meet, what is x and what is t. Alright, so that'll do it for relational motion. Until next time, I'll see you again soon.